Hi, I'm Ruud. I'm a mathematician, work as a senior staff engineer in the Developer Tools organization at Sun Microsystems. I'd like to welcome you to a 7-module training series brought to you by Sun. It's called An Introduction to Parallel Programming. The trend toward multi-core and parallelization is creating demand for new skills from software developers. In this series, we'll discuss parallel programming as one of the fundamentals of application development. Last time we discussed parallel architectures and chip memory design. In Module 4, we will go over parallel programming basics. In this module, I would like to talk about various aspects of parallel processing and parallel computing. To start with, why do we consider parallelization in the first place? Parallelization is another optimization technique. The goal is to reduce the execution time. That's also called the wall clock time, the time on your watch, the elapsed time, in Unix terminology, the real time, as being produced by the time command. That's the goal. We want to reduce the execution time. In doing so, we're going to use more resources. In particular, we're going to use more processors or cores to get to our goal. In this diagram, I'm showing the execution time on one core, and in the ideal case, if we are going to use 4 cores, we can reduce that execution time by a factor of 4. Instead of 100 seconds, my program could now run in 25. And that's a very nice goal to strive for. That's really the goal of parallelization. So what is parallelization? And deliberately I call that something because we can find parallelism at various levels. And I'll show you a little bit of that along the way. The key is that whatever level of parallelism we identify, there has to be independence. Whatever I'm doing at that level should be independent of the order. So if I do 2 things, and I can do them in any arbitrary order, I can also do them at the same time. And if I can do them at the same time, that's parallelism. If there's an implied order, where I first have to do something, and then the next thing, then I cannot do that at the same time, and it's not parallel. It's as simple as that. So it's all about the order of operations. If there's no enforced order needed, then I can execute in parallel and I get my parallelism. And we can find that at different levels. That level is typically called granularity. I could have it deep down in one core even. Many of the cores available today can execute multiple instructions at the same time. Well, that gives me a tiny level of parallelism, but it is parallelism. Again, at a very low granularity. It could be several program statements in my application. I just happen to write them in a certain order, but when I look at it again, maybe I realize that I could do it in another order and still get the correct result. Well, if that's the case, I could execute it in parallel. It could be at a higher level. I could have an algorithm specifically designed for parallelization, or I could find the parallelism at the problem-solving level. For example, a web server where I have multiple independent transactions. They can be executed in parallel, but could also be in a scientific application, of course. I've already mentioned the word thread a couple of times in the previous modules. This is again a loose definition, but I think good enough for our purpose. A thread consists of a series of instructions with its state, like a program counter. So it's in a way the software abstraction to extract the parallelism from the application. A thread is a sequence of instructions that can execute independently with another thread. And that gives me the parallelism. As shown in the diagram here, I have 4 threads, and each can march on independently. They don't need each other. And that gives me the parallelism. Those threads are then scheduled onto the hardware, multiple cores or multiple processors in my system. That scheduling is mainly an operating system responsibility that I will not talk about in this module, but it is something to keep in mind. We have the software running, and at the end of the day, the software has to run on the hardware, and that's under control of the operating system. And some operating systems provide more control than others to control where threads should be running. So the goal is to reduce the wall clock time, the execution time of my program. The problem is that the CPU time, as measured through CPU clock cycles in the core CPU, often exceeds my original serial CPU time. In other words, if I was charged for cycles, my bill would go up. I would pay more because I consume more cycles. If I do a good job, the reward is that I have my results sooner. Why is that? Well, first of all, you don't get the parallelism for free. If you take an existing application, how do you get the parallelism in? Well, depending on what kind of tool you use, at the end of the day, there will be library calls inserted in your sequential application, turning it into a parallel program. You did not have those library calls before, and they'll have to be executed. That's part of what we call parallel overhead, and that goes onto your bill. You will pay extra cycles to execute that. More importantly, is that the threads probably need to communicate. They have to exchange certain types of information. That's generally called parallel communication, or just communication for short. And that was another thing you did not have in your original application. All of that will go into your bill, and the key thing is that you've got to keep those under control. The problem is with communication, it tends to grow as you add threads. So the cost of communication may not be an issue when you go to a dual core system, but when you go to 4 cores or quad core, the cost goes up and up. And then that can get you sooner than later. So it's not only about getting the right result, but it's also about efficient parallelization. And I will touch upon that in various parts of this training. This slide essentially has the same message as the previous slide, now just with a picture. So I have my serial program, and it runs in a certain amount of time, certain amount of wall clock time. And let's say I can break it up in 4 different pieces. If these pieces are independent, I can execute them in parallel, and if there's only a little bit of communication in the beginning, a long period of execution time, and some communication at the end, we call that embarrassingly parallel. These kind of applications, they do exist, and they tend to scale to a very large number of cores or CPUs. You're lucky if that's your kind of application. In other cases, there could be communication as the threads execute. And that's all the yellow that we did not have before. All the yellow will go into my bill. That's the parallel overhead. And like I said, some of these components, they can grow in terms of cost as I add threads. And those are the ones to be careful with. And they may slow me down eventually. Another reason why a parallel program may not perform as well as I expect is called load balancing. In the ideal case, all threads start at the same time and they finish at the same time. The load is perfectly balanced. That's the goal. But for certain types of applications, that may be hard to achieve. So when I have a load imbalance, they all start at the same time, but at a certain point, one thread finishes. There are still three threads that have to execute. So the first thread that finished starts to wait. It starts to essentially burn cycles waiting for the other threads to come in. Then number 2 finishes, and now I have 2 threads waiting for the other 2 threads to come in. And at a certain point, they're all waiting for the last thread to finish. And if that delay, if that wait time is substantial, that will slow me down and will not give me optimal parallel performance. There are ways around it, which is beyond the scope of this introductory talk, but it is a problem that shows up in certain types of algorithms. Another thing I would like to mention is the choice of parallelism. Let's say we have the luxury of having 2 levels of parallelism in an application. Reflected here in parallelism at the pink level, the pink boxes, and parallelism at the light blue boxes. A high level of parallelism or low level of parallelism. An advantage of going, and again, these are all generalizations of course, but an advantage of going for the high level is that it'll give me low communication cost. That's a good thing. On the other hand, in my example here, I'm limited to 5 independent blocks. So no matter how many cores I have in my system, I can only use 5 of those. And that's not a very nice thought. That's fairly limiting, so that's not a pleasant thought. It also tends to be that the higher the level of parallelism, the harder load balancing may be. Again, these are generalizations, of course. If I go for the low level, that could be, for example, at a loop level, deep in my program, I tend to have a higher communication cost, which is not good. That's something to watch out for. On the other hand, I can typically use more cores, so I'm not limited by like a number of 5 in my case. I can go to a higher number. and load balancing tends to be less of an issue. The strategy should be to actually go for this light blue level and be very aware of communication overhead and try to eliminate as much as you can up front and not make it an issue at all. And that brings me to the topic of scalability. How do I measure, how do I know where I am with respect to efficient parallelization of my program? A very common way to do that is to compute what is called the speedup, the parallel speedup, SP. It's very easy. You measure the elapsed time on one thread, you measure the elapsed time on two threads, and divide the number. In the ideal case, the time on two threads is half of what I had before, and the speedup is 2. I can do that for 3 threads, 4, 5, and so forth. And in the ideal case, we see the line shown here as ideal on the chart. That's the goal. Related to speed up, some people like to calculate the efficiency. It's a derived metric. It is the speed up divided by the number of threads that I've used, or the number of cores. And that's in the ideal case 1. If my program is twice as fast on 2 threads, the speed up is 2, divided by 2 is 1, or 100%. So that will be a flat line. They're related. You can look at both of them or one of them. Personally, I prefer the speed up. Now the problem is that unless the application is embarrassingly parallel, eventually it'll be very hard to follow that ideal curve. You start moving away from it, and at a certain optimal point you start losing efficiency and the speed up will get less and less because the overhead starts to dominate. The whole trick is to push that p-opt to the right hand side as far as you can, make it very scalable. Okay. As one word of warning that I would like to give, when you look at speed up, you divide out the absolute time, and certain algorithms tend to be somewhat slower in the parallel version. It takes, for example, more iterations to converge. When you just look at speed up, you don't see that. So I always recommend people to also look at single-threaded time of the parallel version versus the sequential version. Just a little thing to watch out for. In certain cases, we also see superlinear speedup. For example, on 4 cores, the program is 5 times faster. That may seem like surprising. It's a nice bonus, but why is that? Well, when I add hardware to execute my program, I also add cache memory. So I have more cache memory available for my data, and more of my data will fit in the caches instead of the slower memory, and that often explains the superlinear speedup. Again, it's a nice bonus, but of course you cannot count on it. This was a little introduction into a very important concept in parallel performance. It's called Amdahl's law. I would like to decompose my serial time, my T1, the time on one core, into 2 components. The first component, f times T1, is the part that I can execute in parallel. And therefore the other component, 1 minus f times T1, is the part that I cannot parallelize. That's often called the serial time. If I then execute this program in parallel, the first component, the f times T1, scales with a factor of p if I use p cores or processors. And the second part does not benefit at all, because that was the part that I could not parallelize. If I now divide T1 MTP for the speedup, I get a very simple formula. It depends on f and p. And f again is the fraction of execution time that I've been able to parallelize. F could be anything between 0 and 1. If f equals 0, the program is not parallel at all. If f equals 1, 100% parallelizable, it's embarrassingly parallel. For a real application, f is anything between 0 and 1. So now I have a formula to describe the speedup in terms of f and p. Of course, I know how many cores that I've used or how many threads. So once I know f, I can estimate what my expected speedup will be. And that's what I would like to show now. In this chart, I pin it down to 16 cores or CPUs or processors. And I show you the expected speedup for various values of f. F equals 1 means 100% parallelizable, and I get the perfect speedup no matter how many cores or processors that I'm using. F equals 0, that's the light blue line, means no parallelism at all, and of course I will not get any speedup no matter how many cores that I use, because there is no parallelism. I call those the sanity checks. A real application will have an f anything between 0 and 1. So let's look at the light blue line. The light blue line corresponds to f being 99%. In other words, I've parallelized 99% of the execution time of my program. That's a very high number. But what I see, on 16 processors, my program is no longer 16 times faster, it's 14 times faster. A very good result. But as you can already see, I start to move away from the ideal curve. And one thing to keep in mind with Amdahl's law, we do not model the parallel overhead. So in reality, the performance may even be a little less than what I'm showing here, because there is parallel overhead probably. Things get worse if I would parallelize 75% of the execution time. That's the purple line here. No matter how many cores that I use, I will never be more than 4 times faster. And that's why I call Amdahl's law very ruthless. What Amdahl's law says, you have to parallelize a serious amount of execution time in order to get a substantial benefit from parallel processing. But there's also good news. If we look at the early part of this curve for a low number of processors, we see that it's not so hard to get a speed up, even if I haven't done such a good job. And that's what we see in practice. It's not that hard to get, for example, 30, 40, 50% speed up on 2 cores. That's the low-hanging fruit. And maybe that's good enough. But what Amdahl's law says, if you want to go all the way, you have to parallelize a serious amount of your execution time. The good thing is, on any application, you can measure this fraction f yourself. Again, these are approximations, but turned out to be very useful in practice. I can rewrite my formulas to express f in terms of things I can measure. That's shown in the yellow box here. F depends on the uni-thread time, T1, as well as the time on multiple threads, on 2, 3, 4. So I can measure those times, and I know, of course, how many threads or cores that I've been using. And I'll show you a simple example. If T1 is 100 seconds, and I measure the time on 4 cores to be 37, I can put it into my formulas, and what it tells me, the numbers that I've measured correspond to f being 84%. With f being 84%, I can estimate what to expect on 8, and that's shown in the light blue box at the bottom. And it tells me the time on 8 is 26.5 seconds, and my parallel speedup is less than 4. Now for a long time, that was bad news. It meant that I was wasting more than half of my resources. I'm using 8 cores, and my program is less than 4 times faster. But remember, threads are getting cheap. Because at the end of the day, on 8 cores, I still have a performance benefit. And that's being highlighted on this chart. What I'm showing here is the expected performance for an increasing number of cores. I had my T1, that's the light blue bar here, that was my 100 seconds. On 4 I measured 37, and on 8 I measured 26.5. That's still faster. And if a thread is cheap, who cares? And that's actually what I see these days. People care less about that. They say, well, it's still a substantial performance improvement over my 37 seconds. A thread is cheap, so I don't care anymore. We also see that eventually this curve starts to flatten out. So probably it does not make sense to go much more beyond than 8. But again, the fact that threads are getting cheap does change the landscape. I'd like to spend a few minutes on numerical results, especially when you do floating point operations. As you may know from your high school days, with floating point behavior, you get round-off behavior. If you're using floating point data, there's round-off happening in the computer, and that can affect your numerical results. And what I would like to show you that is very natural for a parallel program to have slightly different results because of differences in round-off behavior on floating point data. So I have a simple example. I want to add B, C, D, and E and store the result into A. On a uniprocessor system, I could start by adding B and C, then I add D to it, and then I add E. But if I have a parallel computer, I could do this in parallel. I can add B and C in parallel with D and E, that gives me parallelism. I store these results in T1 and T2, and I add T2 to T1, and that gives me the final result. Algebraically, this is exactly the same. This is exactly the same algorithm. Numerically, it's different though. The round-off behavior is different. The only thing that's the same is that in both cases I add B and C directly. In the sequential case, on the left-hand side, I add D to the combination of B and C. In the parallel side, I first add E to it, and then I add. Well, depending on the magnitude of these numbers, I will see differences in floating point behavior. So the bottom line is, do not be alarmed if you're doing floating point operations and you execute your parallel program and you see slight differences in the results. Of course, there should always be the concern of having a bug in your program. You can never exclude that, but don't be alarmed initially. I've seen too many people that fall into that trap and get really worried, even though it's only a slight change in numerical behavior. Thank you for watching. Please look at the other modules in this series. For more information on how Sun can help you designing parallel applications, please go to the URL listed on this page or send an email to the email address. We would like to get your feedback, and I hope you enjoyed it. Thank you.